Okay, students, this is the teacher summary for Unit 1, Lesson C, Property of Shapes. You should have your reference card in front of you as well as your handout right here, this page, page 7. Let's go to your reference card first. You should have worked for several minutes with your team using translation, rotation, and reflection to make different shapes. So some of these should not surprise you, most of these should not surprise you, about shapes that are created by reflection and shapes that are created by rotation. Again, reflection means just to flip. So if we take a triangle, and it's an isosceles triangle, and we flip it straight over, and it's a special kind of an isosceles right triangle, we can get a square. And if we flip this triangle, we can get a right isosceles triangle. A right isosceles triangle. So right angle, two sides equal. And if we take this triangle and we flip it over that way, we get what's called a rhombus, which is all four sides equal. And if you take regular run-of-the-mill right triangles, you can get isosceles triangles. Taking an obtuse triangle and flipping over, you're going to get a kite. And if you flip over this sideways, again this way, you're going to end up with dart. So those are just a sample of some of the few shapes you could or should have gotten when you were reflecting various triangles. Shapes created by rotation, that's where you rotate like on the midpoint, and you rotate around. A rhombus also can be created by rotation. A rectangle, but a rectangle cannot be made by reflection. Parallelogram. And taking this triangle and rotating it, you could also get a square. So a square is created by both reflection and can be created by rotation. Again, these are only samples. You probably have several more. So out of the various shapes that you saw, basic shapes, which one of them have line symmetry, rotational symmetry, or both? Well, let's take a look at the regular hexagon. Regular hexagon can be folded along that line and come out equal. It could be folded along this line as well. So there's several lines of symmetry here. I'm only going to keep just the one. But yes, it has line symmetry. That's an example. And you see, if you rotate this corner just to this spot right here, it also has rotational symmetry. The kite, you can fold so it has line symmetry, but you cannot rotate it except all the way around to get the same shape. A rectangle, yes, it has line symmetry. Technically it has two lines. Whoops, that's not a very good line of symmetry. Let's try that again. It has two lines of symmetry. I'm just going to leave the one here. And yes, it has rotational symmetry. If you take this and you bring it exactly around 180, that has rotational. Scaling triangle, there's no way to draw a line to get it folded, and you can't rotate it to get the same thing. So a scaling triangle has neither rotation nor line symmetry. Trapezoid, in this situation, you can't fold it and you can't rotate it. So a regular trapezoid, or a normal trapezoid, if you will, does not have either rotational nor line symmetry. But an equilateral triangle has several lines of symmetry. There would be one, there would be another. There's technically three. So it does have line symmetry. And you see that if this point comes up right to here, it would also have rotational symmetry. Square has line symmetry, of course, and of course it also has rotational symmetry. A right isosceles triangle, there's one line of symmetry, but it does not have rotational symmetry. A circle has ultimate line symmetry and rotational symmetry, because technically we would call this all symmetrical for both. Rhombus has line symmetry, a couple of them, and you can see if this rotates half a circle, you also have rotational symmetry. If you have any just a normal quadrilateral but no sides equal, it's not going to necessarily rotate. Isosceles triangle has line symmetry. A scalene right triangle, no sides equal, no symmetry. An isosceles trapezoid, first off, by definition, it means these two legs are equal. So, of course, when you fold it along that line, it has line symmetry. But it does not have rotational symmetry. Parallelogram, be really careful. It looks like it has line symmetry, so I'm going to draw a line this way. But you can see if you fold it, those corners do not match up. So it has neither line symmetry nor rotational symmetry. Regular pentagon, of course, has line symmetry, several of them. That's just one example. And, of course, it has, from moving that point to that point, it would have rotational symmetry. Now, using the concepts that we've studied, let's come to one example of what I want you to do for your homework tonight. So it says right here that we're going to take an isosceles triangle and reflect it along the base. And ask yourself, what is it called? What are all the possible characteristics? What can you find? So isosceles means you have two equal sides, and then the non-equal side is called the base. So that blue would be a base. So what this is asking is if I flip it, and you probably did one of these, you end up with this kind of a shape. Let me outline it nice and dark. Where you have four equal sides. If you have four equal sides, and the sides are both, opposite sides are parallel and congruent, that's called a rhombus. So, knowing that we did this by reflection, you want to try to get some simple characteristics going on here. So here would be one. Let's not overlook the obvious. We have a quadrilateral. I'm just going to write quad with four congruent, that's a symbol for equal, sides. So we have four equal sides. We also know, because all the sides are equal, that these opposite sides have to be parallel. So do a little arrow feathers there. We know that the opposite sides are parallel. So one set and two set. arrow feathers. Let's see what else we can explore here. Because this is a reflection, that means that this base here, that this angle right here, and this angle right here have to be congruent because we reflected. So same thing here, reflected. So we can see that those two piece angles create one congruent angle. So that angle right there is congruent. Let me change colors. We'll call those the orange angles. So in that case, those opposite angles are equal. And then, of course, since this is a reflection, technically this is exactly the same thing. So this opposite angle is obviously congruent as well. So I'm going to just write this. Opposite corner angles are congruent because it's been reflected. Let's take a look at something else, something a little bit more subtle. We know the three angles of a triangle have to add up to 180. So this angle here, this angle right here, and this angle here all have to add up to 180 degrees. Do you see those two angles there? One here, one here. Do you see that you have two angles here? So technically, that means also this. I'm going to make this squiggle angle here because we can transfer that yellow angle over this way and this squiggle angle here. We're going to call those angles neighbor angles. There's a fancy name for that called consecutive. That means to be next to. Neighbor, quote unquote, angles add up to 180. There's a name for that. Those are called consecutive angles. Angles that are next to each other because, again, of the reflection. Same thing here. If you look very carefully, let me switch colors. We know these three angles, 1, 2, 3, add up to 180. And if we take this angle here and move it right there, do you see that? Let me remove this one on this side. That means those three angles also must add up to 180. So again, these are called consecutive angles, angles that are next to each other in this case. Also, this line right here, that's called a diagonal. A diagonal connects two corners of any shapes. I'm just going to write diag there. We see it cuts this corner in half. So I'm going to write here that the diagonal, at least the one given, diagonal bisects the corner angles. That diagonal bisects the corner angles. A couple more observations. We have two acute angles. And we have two obtuse angles. And last one, since this triangle adds up to 180, and this triangle adds up to 180, we know that the whole thing, the whole shape, must sum 180 plus 180, which is 360 degrees. So that's an observation of what can you find out by the motions you've been doing, because there's symmetry, because there was reflection. What kinds of things can you discover about shapes? Use your photographs that you took of other people's posters to guide you through the rest of the homework tonight. Your goal, I'm going to use this symbol, squeeze the sponge, which means I want you to find everything possible. Really think it through. Really get down to the nitty-gritty here. Do the best you can. Find as much as you can about each shape.